Hello, I'm Caroline. Welcome to my channel. In this video today, I'm going to read from this book, The Earth, Oceans, Continents, Universe. And I hope you enjoy it and find it interesting. And I'll dive straight in. The structure of the Earth. 150 years ago, geologists differed in their opinions about what made up the interior of the Earth. Some researchers believed that the inside of the Earth consisted of a glowing ball of gas. Another group held the view that the Earth is made of a number of layers composed of various materials. By collecting and examining rocks from different regions, geologists tried to find explanations for changes in the surface of the Earth. As early as 1835, Sir Henry de Labec, 1796 to 1855, produced the first geological map of Great Britain. In the early 1990s, a very deep hole was bored into the Earth's crust in Germany. However, the project had to be stopped at a depth of 9,100 meters when drilling in brittle rock, and at the end, a malleable mass at 280 degrees centigrade showed that even the most modern technology has its limits. On the Kola Peninsula in the former Soviet Union, engineers succeeded in drilling to a depth of 12,260 meters. There are also indirect ways of solving the mystery of the Earth's interior. These include the investigation of seismic waves that result from explosions or earthquakes, or investigation of the Earth's magnetic and gravitational fields. Seismic waves are reflected deep inside the Earth at places where there is a change in the type of rock, as well as at the transitions from the Earth's crust to its mantle and core. The waves then return to the surface of the Earth, where they can be recorded by seismographs. The speed of the waves and the depth at which they are reflected give us information about the interior of the Earth. Today we know that the Earth is surrounded by a crust consisting of relatively light rock. Below it is the Earth's mantle, which is made up of solid stone on the outside and becomes molten towards the centre. Inside it is the core of the Earth. A distinction is made between the inner and outer core, both of which probably consist largely of iron, with temperatures in the inner core probably reaching levels similar to those at the surface of the Sun. The Earth's crust. Our continents and the seabed are on the outermost layer of the Earth's crust. It is very thin in comparison to the radius of the Earth, which is 6,370 kilometers on average. Beneath the continents, the crust is 20 to 100 kilometers thick. Below Central Valley in California, the Earth's crust is only 20 kilometers thick. It has a thickness of up to 90 kilometers beneath the Himalayas. Underneath the oceans, the thickness of the crust ranges from 5 to 11 kilometers. From the differences in the speed at which seismic waves travel, we conclude that there are different types of rock. Atmosphere nitrogen and oxygen, crust, silicate rock, mantle, silicate rock, outer core, molten iron and nickel, solid inner core, iron and nickel. Between the crust and the mantle, there is a clear boundary known as the Moho discontinuity, Moho discontinuity for short. It is named after Andrija Mohorovic, the Yugoslav seismologist who discovered it. In 1887, Mohorovic, 1857 to 1936, originally a teacher of mathematics and physics, constructed a meteorological station and observed the frequent earthquakes in his locality with growing interest. In 1901, after the great earthquake in Zagreb, he bought the first seismograph for the Zagreb Observatory, of which he was by now the director. Following a further large quake, Mohorovic proposed the installation of a seismographic station. After the first quake to be successfully recorded, in 1909, he wrote his first seismological paper. In analysing seismic data of quakes and aftershocks, he discovered a layer between the Earth's crust and mantle, the Moho discontinuity. The sudden change there of the speed at which seismic waves spread pointed to a particular composition of material at a depth of 5 to 80 kilometres. Long after the discovery of the Moho discontinuity, the structure of the Earth's crust was still being examined by analysis of seismic waves. From the 1950s, experiments were carried out with shock waves from explosions, which could be produced as desired at selected places and specific times. However, the energy of the waves penetrates only as far as the layers of the mantle. The continental crust is more varied and thicker than the oceanic crust. It contains rocks with an age of up to 3.8 billion years. Erosion and deformation, uplift and subsidence have operated on it and produced a varied structure. Much of the surface is composed of sediments and volcanic rocks of low density. Below this is a folded metamorphosed layer of sediment, adjacent to which, depending on the area, there is a granite layer. The deeper parts of the crust contain crystalline and metamorphosed rock layers, extending as far as the mantle. The structure of the oceanic crust is relatively simple. It is divided into just a few layers. Lightly solidified sediment covers the surface. Its thickness ranges from a few hundred meters to 3 kilometers. The second layer consists of hard rock, containing mainly basalt, but also a small proportion of sediment rock. It is 1.5 kilometers thick on average. A third layer, approximately 5 kilometers thick, has not yet been investigated by drilling. It is thought to be either basalt or gabbro. Enormous columns of magma from the Earth's mantle protrude into these layers. The temperature inside the Earth rises with increasing depth. The rise has been calculated as about 30 degrees centigrade per kilometre from the surface. Oceanic crust, basalt. Continental crust, granite. Structure of the Earth's crust: magma column, mantle, oceanic crust of the Earth. The Earth's mantle. Beneath the Earth's crust lies the Earth's mantle. It comprises 67% of the volume and 82% of the mass of the Earth. Our information about its composition derives from seismic waves and volcanic emissions. The Earth's mantle is relatively cool and has a density only 1/3 higher than that of the continents. On the basis of its physical characteristics, it can be divided into an upper and lower layer. An upper mantle consists of peridotite and basalts, among other materials. At depths between 100 and 200 kilometers, a change in the seismic waves takes place. This layer is known as the Gutenberg zone. Researchers believe that this reversal of the waves is a result of the convection currents inside the Earth. Together with the crust, the upper part of the mantle, as far as the Gutenberg zone, forms the lithosphere. Below it, and still belonging to the upper mantle, is the asthenosphere, in which the matter is less solid. It is involved in an exchange with the lithosphere. If matter from the asthenosphere rises at the mid-ocean ridge, it becomes part of the solid lithosphere. Conversely, the ocean floors sink back into the Earth's mantle at the edge of the continents, the so-called subduction zones, and are swallowed up there. In the middle part of the mantle, which has a higher density, the speed of the seismic waves, P waves, also rises. At a depth of about 2,900 kilometers, the lower mantle, which here consists mainly of silicate rock and has a density of 9.4 GCM, borders on the Earth's core. This region is called the Weichert-Gutenberg discontinuity. Mid-ocean ridge, magma outflow, range of fold mountains, change of volcanic islands, the lithosphere, asthenosphere. The Earth's core. Relatively little is known about the core of the Earth. Its distance from the Earth's surface is thought to be about 2,900 kilometers. However, this figure represents a highly inexact approximation, as researchers believe that the core of the Earth is strongly asymmetrical. Seismic waves are able to pass through it only in part, or are diverted by it. Geologists have discovered that the outer core is probably molten, while the inner core is solid. Calculations of the density of the core put it 4 times higher than that of the crust. As iron is the only element within this density, it probably constitutes the main part of the core, with nickel and also sulfur mixed in. The theory has met with general acceptance, as investigations have found that meteorites, debris from other heavenly bodies, have the same composition. According to another theory, the heat set free by solidification of the inner iron core leads to faster convection currents compared with the mantle in the outer core, which influence or cause the Earth's magnetic field. Molten core of nickel and iron. Inner core, solid core of nickel and iron, 2,400 kilometers diameter. Earthquakes. The earth swelled up in the harbour with spray and foam, and the ships at anchor broke into pieces. The streets and squares were filled with whirlwinds of flame and ash. The houses collapsed, the roofs fell to the ground, and the foundations were torn apart. 30,000 people of all ages and both sexes were buried under the rubble and crushed. Voltaire, Candide. In these words, Voltaire described the earthquake of 1755 that destroyed Lisbon and claimed 30,000 human lives. Many contemporaries saw the catastrophe as a just punishment for their sinful way of life. Every year, more than 1 million earthquakes take place on the earth. However, most of them are so weak as to be completely unnoticeable to humans. According to the geographical location of the source, we distinguish between earthquakes and seaquakes. The distinctions between local quakes, close quakes, distant quakes, and far distant quakes correspond to the distance from the source. In a local quake, the observation post is inside the quaking area. In close quakes, less than 1,000 kilometers from the source, in distant quakes up to 10,000 kilometers or even further from the source. According to their strength, quakes are classified as small, medium, large, or global quakes. The most powerful quakes are recorded all over the world. According to the depth of the source, we distinguish between earthquakes close to the surface, normal quakes, and deep quakes. From the source of the earthquake, concentric oscillations travel across the whole Earth. They're called seismic waves. Seismos is a Greek word meaning shaking. The most powerful ground motion takes place close to the so-called epicenter. The movements are analysed with instruments and by observation of the terrain. The most important instrument for measuring and investigating earthquakes is the seismograph. It records the waves produced by the quake. In order to gain precise recordings, the seismograph must have as little contact with the ground as possible, so that constant motions of the earth can be ignored. For this reason, efforts are made to disconnect seismographs from subterranean movements by means of special attachments with springs or hinges. Distances from the source of an earthquake can be established with the help of a seismic time curve. The basis for this is the arrival of various types of wave at specified observation posts at different times. From this data, it is possible to calculate the distance to the epicenter. Today, this is carried out by means of up-to-date computer technology. After an earthquake has been located, its strength as measured in magnitudes is expressed on the Richter scale. The Californian seismologist Charles Richter introduced the classification of the strength of earthquakes in 1935. A measurement of intensity taken from observed efforts of the earthquake and expressing its subjective strength is made according to the Mercalli scale. Time from the beginning of the earthquake, distance travelled from the epicenter kilometers. Seismogram, time difference 4 minutes. Seismogram B, time difference 9 minutes. Seismogram C, S wave, time difference 12 minutes. Causes and origin. In the time of the Greek philosopher Aristotle, it was believed that earthquakes were caused by subterranean fire and storms. In ancient Japan, people believed that the movements of an enormous fish which carried the earth caused it to quake. Today, we have a fairly exact idea of the causes. 90% of all earthquakes are directly connected with tectonic processes in the lithosphere. Most quakes arise along the boundaries of plates. These plates either slide along each other, collide, or break apart. When plates move away from each other, only small earthquakes arise. There are various causes of stronger shocks. When one plate pushes over another, enormous pressure is built up that can suddenly be released at some stage and lead to an earthquake. For example, in Mexico City in 1985, 10,000 were dead. Horizontal displacement can be seen at the San Andreas Fault, which runs along the boundary between the North American and Pacific plates. In the Loma Prieta earthquake in 1989, the North American plate rose by 1 meter, and the Pacific plate moved 2 meters to the northwest. Fortunately, most of the shock waves were absorbed below ground. Movements along a vertical fault line, as for example in the earthquake of 1988 in Armenia, are the most common causes of quakes. In Armenia, the source of the quake was 10 kilometers below ground, but the shock waves penetrated right to the surface. Earthquakes that originate at depths of more than 100 kilometers usually happen at the edges of continents or on chains of islands located close to deep-sea trenches or young volcanic mountains, such as the Japanese islands and the west coast of South America. Here the plates collide, so that the surface, forced downwards, disappears beneath the upper plate into the mantle. The sources of earthquakes are located on a plain sloping from the ocean to the land. They are at depths of up to 700 kilometers. This area is known as the Wadati-Benioff zone. Horizontal movements can also take place in these areas. However, in 1995, parts of Port Island and Rocco Island were displaced by 4 meters. A normal displacement is between 10 and 20 centimeters. Regions further from the edges of tectonic plates suffer from large quakes much less often. Such regions include Northern Europe and the east of the United States. Nonetheless, a quake shook the city of London in 1750, and in 1811 there were several quakes in Missouri. There is still no clear explanation for these earthquakes in the middle of continental plates. It is possible that they are caused by unknown plate boundaries deep in the Earth's crust. 7% of all earthquakes are of volcanic origin. These are so-called eruption quakes. In terms of timing, location and cause, their shock waves are connected with volcanic activity. 3% can be classified as quakes caused by collapse. This happens when the roof of a subterranean cavity collapses. There are a number of ways in which the cavity may have formed. The shock from the resulting central quake has only a short range. Earthquake region. Most earthquakes arise in places where there are tectonic processes in the lithosphere. Here, plates either slide along each other, collide, or break apart. Earthquakes are most frequently caused by movements along vertical faults. Tectonic processes in the lithosphere, movements of plates. And that's where I'll stop the video. I hope you enjoyed this reading, and if you did, I hope you'll join me again for another one soon. Thank you for watching. Bye.